Hi, today's lesson is about torque. Every time you open or close a door, in order to do so, you're actually applying a force at the door, a distance away from the hinges, and this force is actually causing a turning effect on the door, and this force that is responsible for a turning effect is what we call torque. And so today's lesson is about torque. Now, the symbol for torque, this is something you've learned last year. The symbol for torque is the Greek letter tau, and it depends on two quantities. It depends on the force and where that force acts. So where the force acts is taken as the distance between the point of application of the force and where the hinges, where it turns about. So torque is measured in newtons per meter, the force is measured in newtons, and the perpendicular distance is measured in meters. So torque causing a turning effect. So for example, if that is a wheel, in order to get that wheel spinning, one way is to apply a force, and one way you can apply a force is by wrapping a thread or a rope around the wheel and pulling that rope down. So pulling that rope down is actually tension force, and it's acting at the rim of the wheel, so it's at the distance r from the center of the wheel. So the r could be replaced by d in a formula. So you could have the formula for torque as torque equals F times r. Okay, so if you have several torques acting on an object, you could have the object in equilibrium. That means the torques on it are all balanced. So when torques are balanced, we say that the object is in rotational equilibrium. So if something is in rotational equilibrium, then two possible things can happen. One is it's stationary, it's not moving at all, and the other, it's spinning with constant angular velocity. So two possible things. So on the other hand, if torques are not balanced, then you're going to end up with the unbalanced torque or the resultant torque. And when there is an unbalanced torque, just like we learned Newton's second law for linear motion, this is going to cause angular acceleration. So an unbalanced torque produces angular acceleration. So torque is proportional to angular acceleration, and the constant of proportionality is represented by the letter I, which is actually the rotational equivalent for mass. And this mass is actually called linear inertia, and this I is called rotational inertia. So that's a new term that we've learned today, rotational inertia. So what on earth is rotational inertia? It tells you how hard it is for an object to start spinning or stop spinning, or how hard it is to change the angular velocity of an object. Just like the more massive an object is, the harder it is to get it to move or stop it moving. So it's a similar sort of concept, but there is a little bit of difference. So what does rotational inertia depend on? It depends, yes, on the mass, but it also depends on how far is the mass from the axis or the center of rotation. So rotational inertia actually has a formula, I equals kmr squared, where k is called the shape factor, and it's usually a constant, a number, and it can be anything 1 or 2/3 or 2/5, depends on the shape of the object. M is the mass, and r is what we call the distance of the mass from the axis of rotation. So how far is the mass distributed? And just looking a little more at rotational inertia and how it's applied, it's really, it's very interesting, because if you watch a diver performing somersaults, you find that quite often when you want to do those spins or rotation before entering the water, the diver will actually curl up, okay, makes its body curled up so that they're spinning around their center of mass. And why, the reason why they do that is when your mass is close to the axis of rotation rather than spread out, then it's easier to spin. Rotational inertia is less, so it's easier to spin. And then you also notice that when before entering the water, the diver whose body was curled up kind of straightens out the body and before entering the water, and when he straightens out the body, he stops spinning. Okay, so when you straighten out the body, what actually happens is that his rotational inertia increases, so it's harder for him to spin easily. Then you would also notice lots and lots of examples of rotational inertia, and you'll also find that ballerinas, when they do the pirouette, when they spin around, you find that when they clutch their hands across their chests, they're able to spin much faster, so the acceleration is more, they're spinning faster. And whereas when they spread their arms out, then their mass is spread further from the axis of rotation, so they spin slower. There's also the example of tightrope walkers. So you find that if you're at a height and walking on a ledge, what you normally just involuntarily do is you stretch your arms out. You stretch your arms out because you think, oh, I get better balance. And that's quite right. Because where do you pivot against? You're actually pivoting against your heels, your ankles. Okay, so in order for stability, if you stretch your arms out, then your mass is spread further away from your axis of rotation. Your axis of rotation is about your center, so there's less chances of you twisting and turning. So that's where rotational inertia comes in useful. So that is today's lesson about torque, balanced and unbalanced torque, and how when torques are balanced, you have rotational equilibrium. However, when you have an unbalanced torque, it produces acceleration, and the equation is tau equals I alpha, where I is called the rotational inertia of an object, and it is how hard it is to get an object to start spinning or stop spinning. And we also learned that rotational inertia depends on two factors. It depends on the mass as well as mass distribution. Okay, so I'll put a few more things. Now, the important thing is just make sure you do the questions every day. And if there's anything you don't understand, please feel free to ask any of the physics teachers. We are more than happy to help you. So bye for now and enjoy the rest of your day.